Okay, welcome back. So in this video I'll be talking about the Spherometer. So in the last few videos I've been talking about the vernier caliper and the micrometer screw gauge, and like those two instruments the Spherometer is also used to measure length. But the Spherometer is mostly used to measure special lengths. For example, if you want to measure the length or the radius of a particular lens, we use a Spherometer. So Spherometer is in a way a special instrument. Alright. So let's take a simple introduction. I'll give you a simple introduction about the Spherometer. So here's a sample Spherometer. So I will introduce you about the concepts and the parts of the Spherometer in the next few slides and in this next few minutes. So Spherometers are used for small precision instruments or small precision measurements. For example, if you want to measure the radius of curvature, you can use a Spherometer. So Spherometer is a very limited instrument. So that is one of the greatest disadvantage of a Spherometer. For example, you can't use a Spherometer to measure the depth of something. For example, the depth of a test tube. And also you can't make it to measure the external and the internal widths of an instrument because there's no span here, right? It can be only used to measure the height of something. It can be used to measure the length, because what you do is you rotate this. We call this the screw or the middle nail. You rotate this and the screw, now this knob like thing is connected to this small part, right? Is connected to this small part, and when you rotate this in the clockwise direction or the anti-clockwise direction, this goes up or down depending on the direction of rotation. So it can be only used to measure the height of something. It can be used to measure the length of something. However, Spherometers are very useful in the concept of measuring the radius of curvatures. That's why I mentioned here to measure the radius of curvatures. Opticians use it very much, the Spherometer, as a measuring instrument for very precise measurements for lens. Also, if you want to measure the thickness of something, for example, if you have a glass cube or a similar instrument where you need to find the thickness, you can easily measure it using a Spherometer. One of the greatest advantages of using a Spherometer is that for most Spherometers, the error of measurement is so minimized that you can ignore it. That is the reason is that one of the reasons is that you can measure only one measurement, that's the height, and the other reason is that when it is manufactured, this vertical scale is actually this circular scale. The circular scale is actually slant to this meter scale. For most of the Spherometers, you can see that the zero of this circular scale will not probably coincide with the zero of the meter scale when it is intact. So what actually happens is that although at the moment of production, most of these producers, what they do is that this circular scale is they make it a little above the zero mark, so that the zero of the circular scale is naturally a little bit above the zero of the vertical scale. So due to this reason, even at the first instance you are using a Spherometer, you can ignore the errors in measurement. So that's one of the greatest advantages of using a Spherometer in measuring the height, because in the case of a micrometer and the screw gauge, you have to consider when there's a zero error. Alright. So as in the micrometer, screw gauge and the vernier caliper, I will next explain you about the parts of a Spherometer. A simple Spherometer looks like this. So there's a screw head here, there's the circular scale, there's the vertical scale. So and here's we call the base circle or the basement, and there are three legs that make an equilateral triangle. So that I'll explain in the next few slides about the formation of an equilateral triangle by the legs. and we also call this the middle screw or the leg, middle screw or the central leg, then that is connected to the screw head via the circular scale. So when considering the vertical scale can be divided into three parts. That's the zero of the vertical scale, the positive part, and we call this actually the negative part. You can take measurements of negative parts, but we call for simplicity the negative and the positive part. We don't make it the negative and the positive, we call it just for simplicity. So this part that is above the zero is used to read the radius of curvatures or the heights of convex surfaces, or you can use it to measure the height of some object, in which it can be used. For example, if you keep a block of glass and you want to find the height or the thickness of that glass, you can find that. The latter part, the down here part, is used for concave surfaces when you want to measure the radius of curvature of a concave surface, and if you want to measure the depth of something, depth of an instrument in which the depth is not very high, if you can assume that the depth can be measured using the spherometer, it is very easy, because it's a great advantage or a great leap over the vernier caliper in which we normally use to measure the depths and we have been using so far, because in the case of a spherometer the zero error should not be generally considered. Alright, and it's easy. So those are about the parts of a spherometer. So what actually happens when you are using a spherometer is that you keep the legs. First of all, you need to make sure that you keep the central leg and the legs, these three legs, in a single plane, so that they actually, if you keep it on a table or on a glass, they are actually touching. All those legs are just touching. None of the legs are above another, and that's the most important step. And what you do is you rotate this screw head so that this circular scale rotates about the zero vertical scale. So the vertical scale, as in the micrometer screw gauge and the vernier caliper, is fixed to this base circle, and the circular scale is the movable part. And we don't normally call this the vernier scale, we just call the circular scale because it's not a vernier thing that we use here. So when you rotate this vernier scale using the vernier and the vertical scales, you can take the measurement. So let's see as to how we can do that. Before explaining you about the measurement that we can take using a spherometer, I need to introduce some special terms. Actually, I introduced these terms in my video on micrometer screw gauge, and it's not a new term. These two terms, the pitch and the least count, are not. Least count was also used in the video on vernier caliper, and the pitch I used in the video on the micrometer screw gauge. So these two terms are not new to you. So again, I'll remember, just as a reminder, I'll tell that the pitch is the distance moved by the middle screw per revolution. When you rotate the screw head 360 degrees, this circular scale will move some distance, and the distance that is moved in the vertical scale, moved in the vertical scale from 0 to 360 degrees, that's through one revolution, is called the pitch of the spherometer. And the least count is equal to pitch divided by the number of divisions on the circular scale. For example, if you have a spherometer of 0 equal divisions and of pitch 0.5 millimeters, you can say that the least count is equal to 0.5 millimeters divided by 100, which is 0.005 millimeters or 0.05 centimeters. Alright, so I explained to you at the beginning what are the uses of a spherometer. So one of the greatest uses of a spherometer, and widely used purpose of the spherometer, is that you can use it to measure the radius of curvature. So what is the radius of curvature? If you take a curved block like this, and if you have now this line used to separate this, is we can use this either as now in this case we can use it as a concave surface, and also sometimes we can use it if you separate it in a different way along this circular cube, you can also use it as a concave surface. Now this is a convex surface, you can also use it as a concave surface. So convex surfaces and concave surfaces can be separated out by this line, and the radius of curvature of such a convex or a concave surface is the radius of the sphere that was used to make it. So if this is a curved block, this is the radius. This is not actually the radius, this is the radius from here to here. So if you have a curved mirror like this, there are ways to measure the radius. So there are actually scientific methods to measure the radius, but for most often, although they are because they are very complicated and sometimes they are not useful and sometimes they are not well versed with the techniques we are using, we normally use a spherometer to do that. So to measure the radius of curvature of such a concave or a convex surface, what you do is that we place the mirror on some paper or on the table, and we keep the spherometer like this, and we take the measurement. So I will explain about taking the measurement in my next slides. So first of all, before explaining you about the concept of taking measurements, I need to explain to you about the expression that we are using to take measurements. So in the case of the vernier caliper and the micrometer screw gauge, I explained to you as to how we can build up an equation so as to take the measurement of any measure. You can take the measurement of 10 centimeters, 20 centimeters, of a concave surface, of a convex surface, of a flat surface, anywhere. So we need to find a general equation for that tallies with most surfaces. To build up an equation, what we do is that we just keep the spherometer as it is when taking a measurement, and from the Pythagoras theorem you can see that this is a right angle triangle. You can say that the r squared here is equal to x squared here. So r is the radius of curvature, so this is the center. So this distance, you know that the radius, now this distance is equal to this distance, the blue distance here, from here to here, and from here to here the radius is equal, right? So this distance is r, this is r, and this is r, and this is the central leg like this, and you can use it. So I'll call this length the height. So that's the height, means now these are the central leg, these are the legs, these are the small legs that we are using, and this is the central leg of the middle screw. The distance between the legs and the screw I'll take as the height h, right? So if h is the height, I can say from Pythagoras theorem that r squared is equal to x squared plus r minus h squared. So that's from the Pythagoras theorem. However, we cannot practically measure x because x is the distance. If you actually do this practically, you may have understood, or you may have seen that it's very hard to measure the distance from a leg to the middle screw. You can measure the distance, but you will not get the value of x here, because x in this case is an internal measurement that has to be measured inside this concave surface, right? So what actually happens is that we cannot practically measure x, so we build up another relationship between x, h and r in order to make this equation simpler, and in order to make this equation possible to take measurements. So when you keep the spherometer on any surface, the legs will form an equilateral triangle. So I explained to you that a little while ago as well. So when you keep that on the surface like this, these three legs will now form an equilateral triangle. You can measure that. You can measure these distances easily using a vernier caliper, so that now it is not very precise to measure using a micrometer screw gauge, because this pressure, you need pressure here, so you don't need to consider the negligence of pressure here, because these are steel, not like in the case of paper or rubber. You can apply pressure on steel so that the steel will not deform its shape. So what actually happens is that you can easily use a vernier caliper to measure these distances, and you can verify that they form an equilateral triangle, right? So when measuring the distance, they will form an equilateral triangle like this. So this angle is 60, so this is the angle bisector I have taken this, so this is 30 degrees, so this is actually geometry, right? So if you're not interested, you can just generally take the equation. So this is actually the derivation, right? The derivation. So what actually happens is that you can say that r squared is equal to now a squared by 6h plus h by 2. You can deduce that using x 30, and from the cosine relationship we can finally find a value, substitute a value for x using a. A is the distance between these two, between any of these legs. So if it is an equilateral triangle, all these lengths are equal. So x, we can find that x is equal to a by root 3 by solving this using trigonometry. And finally you can say that r squared is equal to h squared by 6h plus h by 2. So that's about the general equation that we normally use to find the radius of curvature. Now you can find the value of h. You can find the value of h easily. You can also find the value of a easily using the vernier caliper. So using that equation, you can finally find the radius of curvature of such an object. So when measuring the radius of curvatures, there are two types. One type is the convex surface, like this. So we measured that, the convex surfaces, so that's the one we just found. And the other type is the concave surfaces. So concave surface is upside down of the convex surface. So when measuring the concave surfaces, as I mentioned at the beginning of this video, you have to make sure that the circular scale is below the 0 mark. Now you know that this is the central line. If you keep it on a table or on the on a glass or on a paper, these legs and the middle screw will be planar, so that they will be on a single line. So if you want to measure concave surfaces, what you have to do is that, if first of all you need to keep this in a single line, and you have to not take it upwards, you have to take it downwards, right? So that the some point that coincides with the circular scale, the vertical point that coincides with the circular scale, will be below 0. You can easily do that if you do practically using a spherometer. So this is about measuring the convex and the concave surfaces. So now, having explained about the convex and the concave surfaces that we can use to measure, now let's consider about the methods of using. Now, as I mentioned in the first part of the video, you need not to probably consider about the error that could happen when taking a measurement using a spherometer. That is because the spherometers, as I mentioned, are produced so that to minimize error at the production, the 0 of the circular scale is possibly above the 0 of the vertical scale. That's not the way that is generally expected in the case of the vernier caliper and the micrometer screw gauge, but in a spherometer it's completely contrast to those occasions. So the first step, you don't need to consider the error. So the first step is that we need to know whether, when taking the measurement, that this middle screw or the middle nail or the central leg is in a planar position with the other 3 legs. You can do it by a simple experiment like this. You can take a simple plain mirror and you can keep the spherometer on that. You can take the middle screw into some distance, and now you can see that the image of, now this is the object. Now I am considering this object and its image. You can see that this is the object, the central leg or the middle screw or the middle nail, and its image doesn't match. Doesn't match means this point does not coincide with this point, so as any other point on the middle screw doesn't coincide with this one. But if you take it downwards, at some position you may see that every position makes it coincidence. This point coincide with this point, so the distance between this point and any other point like this will be the same distance between this point and this point, right? So this is actually a simple experiment of light, and I will not explain about the images here. So this is a simple experiment that you can do to make sure that the central leg and the other 3 nails are in a planar position. So that's important in taking a measurement using the spherometer. I will explain why. Then what actually happens is that The second step is the reason as to why I took the first step. When you keep the spherometer on such a surface, what you do is that you first of all read the measurement. You can say that probably sometimes it might be 0 0 position. 0 of the vertical scale may coincide with the 0 of the circular scale, but for most measurements it may be not so it's not a problem. So as I mentioned, not as in contrast to the vernier caliper and the micrometer screw gauge, you don't need to make sure that the 0 and the zeros are intact. So you need to make sure that the measurement you are taking, X, or the first measurement you are taking, is so that the central leg and the 3 nails are in a planar position, and you have to take that. So that's the reason as to why we need to make sure that those 3 are planar, and by keeping it on a mirror we have to make sure that. So what actually happens as the third step is that you keep the spherometer as it is, you don't move it. What you do is you rotate the screw head. You rotate the screw head so that the screw goes up. The screw goes up some distance, and then what you do is as the fourth step, you place the object. Now this is very similar to the measurement that you are taken using the vernier caliper or the micrometer screw gauge. In the vernier caliper, as I mentioned in the video on the vernier caliper, what you do is that you move the movable jaw so using the fine adjustment screw so that the object can be placed, and then you move the fine adjustment screw in the other direction so that there is a simple pressure exerted between the fixed jaw and the movable jaw. In the case of a micrometer screw gauge, what you do is you move the ratchet so that the spindle moves some distance. You keep the object on the anvil and you move the ratchet in the opposite direction, so there's a small pressure build up between the anvil and the spindle with the object. So in the same sense, in the case of a spherometer, what you do is that you take the screw head upwards some distance, and then what you do is that you keep the object and you take it downwards. At the moment the screw head is intact with the object, you measure the height or you read the coincident point of the circular scale and the vertical scale. So you say that the height of that measurement, as you can take it to be y. So you can say at the beginning when it was kept on a plane, you can say the measurement you took was x, and when you took to a height and then you kept the object, and when you placed the middle screw on the object, the height was y. So the height of the object should be the difference between these heights, which is y minus x. Now to measure the radius of curvature, if the object is a spherical object, we have to measure the distance of using a vernier caliper. This is because you know that although we measure the height of such an object, you see if you want to use the equation of r squared equals a squared divided by 6h plus h by 2, you need also to find the value of a. So a is the distance between any two legs. Since the three small nails form an equilateral triangle, you can measure the distance between any of these legs, because the length between any of these legs is the same. So you can use a vernier caliper to do that, because as I mentioned a little while ago, the micrometer screw gauge is not the best option, because there's pressure. You need pressure here. This is an occasion you need pressure, and you can use a vernier caliper to do that. And if you are going to find the radius of curvature, so if you don't want to find the radius of curvature, so for example, if you want to find the height of a glass block or the thickness of something, you can terminate actually the experiment at the 6th step. But if you want to continue with this experiment in order to find the radius of curvature, you can go to the 7th and the 8th steps, and at the last step you can find the derived formula and find the radius of curvature, since you know the values of a and h. So that's it about the spherometer. So in this video I explained to you about what is meant by a spherometer, what you can do with the spherometer, what are the measurements that you can take with the spherometer, and you need not to consider the error. You can make it negligible. What are the parts, what are the special definitions, how we can take the measurement using the spherometer, how we can build up a relationship for the radius of curvature, which is actually the main thing that we do using a spherometer, and finally how we can take measurements using the methods I described a little while ago. So that was about the spherometer. So in the next video I'll be talking about another practical that we normally use under physics. So thanks for watching this video, and see you then.